How are y'all doing today?
Morning. Doing well, thank you. How are you doing?
Doing well. So today we're going to be talking about the transient analysis of parallel RLC circuits, I believe. So I put on Moodle a kind of printout thing. Let me see if I can pull it up real quick. Let's see, share screen. Class meeting 7. This table of parallel and series RLC responses. And so we're going to be using this table for the next 2-ish weeks to figure out how these kind of circuits behave. Now, I believe in the online lecture that I put up, I effectively derived the equation for the overdamped response, which I have here as y of t. So that's going to be our overdamped response, a1e to the s1t plus a2e to the s2t, and then plus y at infinity. That's going to take care of our forced response bit that we're going to get into, I think, next Tuesday. But I did not derive the equations for the response of critically damped circuits and underdamped circuits. And the reason I didn't do this is because they're actually the same thing, but just for different circumstances. What I mean by that is if we look at the response for a critically damped circuit, we have a1t e to the minus alpha t plus a2 e to the minus alpha t. The response looks like that because S1 and S2 are identical, and because we have a second initial condition that we need to satisfy, that's where that extra term of t comes from in our first coefficient. I mean, if you've had a class on linear systems and signals, like I believe most of you biomed students have had, that should be familiar with you. Similarly, if we look here for the response of a underdamped circuit, where it becomes y of t becomes b1 cosine omega dt plus b2 sine omega dt, that whole thing multiplied by e to the minus alpha t. That occurs when S1 and S2 are complex conjugates of each other, and instead of dealing with complex numbers, a few trig identities were applied to fix that. So it really does all boil down to this one equation for the overdamped response where we derived it. Okay. So what I would like for us to do today, unless anybody has any other ideas, is to work one of the homework problems that's assigned on this material, which I just put that homework set up within the last 5 minutes, so you likely haven't had a chance to look at it. That's my fault, but I feel like working one of these problems will probably help solidify things a bit. So to that end, let's get started. Let's see. So we have a parallel RLC circuit where the switch is changing from position A to position B at t is equal to 0, and that switch closing at position B effectively places the 0.1 farad capacitor, the 2 ohm resistor, and the 1.6 Henry inductor all in parallel with each other. So that's why we have a parallel RLC circuit. Our method for solving these circuits is very algorithmic. We're going to do the same basic steps in the same basic order every time in order to minimize mistakes, just like we did with transient analysis problems for first order RLC circuits. So the first thing that we need to do is we need to calculate the value of alpha, what's known as the Neper frequency of the system, and omega naught, which is known as the resonant frequency of the system, and compare them. And that comparison will tell us whether or not the circuit is overdamped, critically damped, or underdamped, and it will let us know which response equation to use. So from our table, for a, let me get my pen going right. For a parallel RLC circuit, alpha is given as, I believe, 1/2 RC. Yes. So in this case, that's going to be 2 times 2 ohms times 0.1 farad, this whole thing to the -1 power. So that's 4 times 0.1 is 0.4. So 4/10, so 10/4 should be 2.5 with units of nepers per second, if I did my math right. Desk is a bit of a mess right now. So let me just double check my mental math on that. Yep, 2.5 nepers per second. And omega naught is 1/√LC. So that's going to be 1.6 henries times 0.1 farads. This whole thing to the -1/2 power. So we're taking the reciprocal and we're square rooting it. And we also get a value of 2.5. And the units on our resonant frequency are radians per second. All right, so since alpha and omega have equal values, what does this mean with regards to whether the circuit is overdamped, critically damped, or underdamped?
Should be critically damped, right?
Yeah, when alpha and omega naught are equal, the circuit is critically damped. So damped. And we're going to use that in part D to develop our mathematical expressions. All right, so part B asks us to analyze the circuit at t is equal to 0- and determine the values of the voltage labeled as V, and then our resistor current, our inductor current, and our capacitor current. So at t is equal to 0-. Circuit's going to look something like this, where we have our 12-volt source. So I'm going to have to go back and forth and look at things. 5-ohm resistor. Our capacitor is going to look like an open circuit because we are at DC steady state. That's where our capacitor was. Then we're going to have, let's see this, our switch is also open. So we're going to have an open circuit there. So we'll have our 2-ohm resistor here. Our inductor will look like a short circuit. Here is our inductor current, IL at 0-. Here is our resistor current, IR at 0-. The voltage drop, V, is the voltage drop over the resistor effectively. So what I'm going to do is I'm going to move that 2 ohms over. And finally, we have our capacitor current IC at 0 minus. So which of these parameters can we get without really doing any circuit analysis whatsoever?
Pretty much all of them, right?
Yeah, in this case, pretty much all of them, but specifically with no circuit analysis whatsoever, we know that IC has to be equal to 0 amps because it's the current flowing through an open circuit. And we know that V 0 minus has to be equal to 0 volts because it's the voltage drop over a short circuit. Since that 2 ohm resistor and the short circuit are in parallel, they have the common voltage, so V of 0 minus is also 0 volts. From this, we can then tell that IR at 0 minus is going to be 0 amps because if there's no voltage drop over the resistor, there can't be any current flowing through it. And we can apply Kirchhoff's current law at our bottommost node and easily see that IL at 0 minus must also be 0 amps. Does that circuit analysis look good to everybody?
Yes, sir.
All right. So at t is equal to 0 plus, do I have space? Yeah, I do. Okay. Our circuit is going to look like, so when that switch disconnects from point A and closes to point B, that's effectively removing the 12 volt source and the 5 ohm resistor from affecting the parallel RLC circuit, but I'll go ahead and draw them in just for the sake of argument. So we're going to have an open circuit there. Let's see, so we have a, excuse me, one thing that we didn't really take into account, which is going to be important here, so we'll have to circle back to it in a second, is the capacitor voltage, which is different than the V naught that we've, or the V that we've defined, but I'll explain that in just a second. And then our inductor is going to go over here. So our 2 ohm resistor is going to remain being a 2 ohm resistor. What's going to happen to our inductor?
It's going to change to a current source.
A current source having what value?
0 amps.
So what's a better way to draw a current source with 0 amps of current flowing through it?
Short circuit.
No, open circuit.
Ah, right.
All right. So let's look back up here and make sure that we haven't made a mistake about how V is defined. No. So V is defined as the potential difference between this node and this node, right? So V is the voltage drop over the resistor. So, ooh, crap, how do I undo that? So we're also going to need to figure out what this voltage VC at 0 minus was, because that's going to influence how our circuit behaves at t is equal to 0 plus. Does anybody have any idea what that might be?
12 volts.
12 volts. So that's correct, because since there's no current flowing through the 5 ohm resistor because it's not part of a closed current carrying path, the voltage drop over the 5 ohm resistor is 0. So a simple KVL loop, sorry. Need to turn my ringer off so my wife's texts aren't so dang loud. All right. So we can do a simple Kirchhoff's voltage law loop around the left-hand side of the circuit there and find out that VC at 0 minus is equal to 12 volts, and then we can apply that here. So our capacitor now looks like a 12-volt source. So this is V at 0 plus. Here's IC at 0 plus, IR at 0 plus, and IL at 0 plus. All right, so IL at 0 plus is going to be 0 amps. The current through an inductor cannot change abruptly. So whatever IL was at t is equal to 0 minus, it has to be the same at t is equal to 0 plus. V at 0 plus is going to be 12 volts. The capacitor voltage can't change abruptly, and a V didn't represent the capacitor voltage before the switch closed, but it certainly does afterwards. So VC at 0 minus has to be equal to V at 0 plus. All right, so let's look at IR. So we know that there's a 12-volt drop over the 2 ohm resistor because it's in parallel with our capacitor. So 12 volts divided by 2 ohms gives me 6 amps. And let's see, IC at 0 plus must be negative 6 amps because the current that flows down through the resistor is going to see that node at the bottom, and it's going to split, and or it's going to, all of it's going to flow to the left because it can't flow through the open circuit and then flow up through that leftmost branch containing the capacitor. So the 6 amps of current is flowing in the opposite direction as IC at 0 plus is defined. So that's why we get negative 6 amps. So all my circuit analysis look okay here.
Yes, sir.
Any questions or anything?
Not yet.
Okay, great. So part D. Because our circuit is critically damped, that means that the response will be of the form y of t is equal to a1t e to the minus alpha t plus a2 e to the minus alpha t. So the question is, what response do we want to determine? So if we look back here, we're asked to determine an expression for the voltage V of t, which is the capacitor voltage, so that's a good place to start, and our resistor current I of t. Okay. So since the circuit is critically damped, we know that V of t will be of the form A1, t e to the minus alpha t plus A2 e to the minus alpha t. V at 0 plus will then reduce to, so at t is equal to 0 plus, this factor of A1t goes to 0. So we have 0 multiplied by e to the minus alpha t, so that's still 0, plus A2 times e to the minus alpha times 0. So that's e to the 0, which is 1. So V at 0 plus is equal to A2, and V at 0 plus was 12 volts. So we've already determined one of our 2 coefficients. So things are working out pretty swimmingly thus far. I'll put a box around this guy for now. We'll have to come back to it in a minute. All right. Now we need to develop another relationship to figure out what A1 is. So V here representing the voltage drop over everything, but specifically I'm going to look at it as effectively the capacitor voltage. I'm going to use now the capacitor current because it has a derivative-based relationship. So the capacitor current, by definition, is C dV by dt, which is going to be C multiplied by whatever it is that my table has for the derivative. So that is negative negative alpha A1t e to the minus alpha t plus A1 minus alpha A2 e to the minus alpha t. And IC at 0 plus is going to cause this expression to reduce to, so that whole first term right here is going to go away because we're multiplying by 0. So we're going to have C multiplied by A1 minus alpha A2 and e to the minus alpha t reduces to 1. So this is our expression. So let's see, C was 0.1 farads. A1 is still unknown, minus 2.5 units per second, or nepers per second, times A2, which is 12 volts, will equal to IC at 0 plus, which is minus 6 amps. And we now have one equation, one unknown. So this should allow us to solve for A2, excuse me, A1. So give me just a second. (0.1) times x minus 2.5 times 12 is equal to negative 6. I get A1 is equal to minus 30, and the units of this guy should be volts per second. It may not be intuitively obvious here, but if we notice, we're having A1 minus something in units of per second multiplied by something in units of volts. So A1 needs to have units of volts per second. Also, if we look back at our original response equation, here A1 is a factor that's multiplied by time, and it's giving us volts because we're looking at voltage. So A1, the coefficient, needs to have units of volts per second. So everything's working out hunky-dory there. So from this, V of t is negative 30 t e to the minus 2.5 t plus A2, which was 12 e to the minus 2.5 t volts, where we're just plugging our values for A1, A2, and alpha back into this response equation. So any questions thus far? All right, nobody's saying much of anything. So I was also asked to find an expression for IR of t. How am I going to do that?
Should be the same life pretty much, right?
So this is an important point about the solving RLC circuits, whether they're series, parallel, or general. So the relationships that we use to get an analytical expression for the voltage response here, we were able to do that because we know that the voltage drop over the capacitor and the current flowing through the capacitor have a derivative-based relationship between them. They also have an integral-based relationship, but I don't like doing integrals, so I never use those. So our first equation came from our capacitor voltage, and our second equation, this guy, came from our capacitor current, where we were able to apply a derivative-based relationship, this guy here, to get it. For a resistor, there are no derivative-based relationships. So we can't actually go through this process like we've done to determine the capacitor voltage. Instead, let's look at our original circuit. So this is a parallel RLC circuit. When the switch is closed, the voltage drop over the capacitor and the voltage drop over the resistor represent the same quantity. True or false?
True.
Okay. So if we know the voltage drop over the resistor, how can we find the current through the resistor?
Divide the voltage drop by the resistor.
Yeah, just use Ohm's law. Absolutely right. So IR of t is just going to be V of t divided by 2 ohms. So it's going to be negative 15 t e to the minus 2.5 t plus 6 e to the minus 2.5 t amps. So we're never going to be able to solve for a resistor quantity first. We're always going to have to use either our inductor current relationship or our capacitor voltage relationship, and then do a little bit of circuit analysis to figure out what's going on with our excuse me, resistors. All right, that took half an hour. Let's model our results using Ltspice. Specifically the results of what's going on at t is greater than 0 plus. So let's stop sharing that, start sharing Ltspice. So let's see, I have a capacitor. I have a resistor, and I have an inductor. The value of the capacitor was 0.1 farad. The value of the resistor was 2 ohms, and the value of the inductor was 1.6 henries. Oh, and I don't think it'll matter here, but I'm going to set the series resistance of the inductance to be equal to 0. I might have taken the problem out that was causing issues with, but I don't remember. I'm going to wire all these guys up. Stub here, ground the bottom. All right, and I'm going to need to put in my initial conditions. So the initial condition on the capacitor voltage, which will be the voltage at node 1 with respect to ground in this circuit, and I know that emphatically because there's only one node that isn't ground. So what was the initial condition on my capacitor voltage?
It was 12 volts.
12 volts, all righty. Control M for new line. The initial condition on my inductor current was 0 amps, I believe.
Yes.
All right. And let's see, alpha is 2.5 per second. So 2.5 cycles per second. So I'm going to look at this thing for, let's say 5 seconds then. Wait, on 2.5 cycles per second. 2 seconds, so I can see roughly 5 cycles. Edit simulation command 2 here. All right. So let's look at our capacitor voltage first. So we're not actually looking at it quite long enough to see it settle down to 0. So let's change this guy. Just 3 seconds. So when I ask you guys to verify the behavior of a transient analysis problem, my expectation is that we're going to be able to see the signal settle to its final value, which in this case should be 0. But I don't want the length of time to be so long that we can't actually see the transient behavior. And so let me explain what I mean by that real quick. So let me close this. So right now, if you can see my cursor over here, the voltage is still increasing, so it has not settled to its final value. I was going to change it to 3, but instead I'm going to change it to like 20 real quick to explain why I don't want this. So when I look at it at over a time interval of 20 seconds, effectively everything from 4 seconds and beyond is useless information because it's entirely redundant. So I can still see vaguely what's going on, but the overwhelming portion of my graph is uninteresting material. So this one wouldn't be that bad, but I very often have students do dumb stuff to where, let's do it 200. Where they just put it for a really long amount of time, and then they see it do something like this, where you can't actually see the nuance of what the circuit is actually doing. So if you do something like this, just know I do not like it, and I will count off all of the points. So let's circle back around and put it at 4 seconds, because that looked good. All right, so we can see that it's settling to 0 at somewhere around 3 seconds. We got a little bit of extra information, but nothing horrible here. All right, so in order to make sure that this is mapping correctly, I'm going to add a trace. And I had, I believe, -30 times time times exp of -2.5 times time plus 12 times exp minus 2.5. And we can see that these curves match exactly because the blue curve completely overlaps the green curve, which is what I want. But I also need to make sure that my scale on the left-hand side, which is ranging from +12 to -2, matches the scale on the right-hand side, which is ranging from +12 to -2. So I have used my circuit simulation tool to verify that my analytical solution, what we did on paper, as it were, is completely matching what we saw for the simulation. We could, for the sake of argument, go ahead and verify the resistor current as well, but I'm going to take off this because it's going to get too busy with so many signals. So current probe, resistor current going down, add traces. So this was -15 times time. And of course they match as well, because I'm really good at dividing by 2. Okay, so any questions on this, this stuff, either the simulation portion or the analytical solution portion?
Got a quick question on the simulation portion.
Sure.
Whenever you ask us to verify it, you want like screenshots of both or of all possible values or equations that we get with the answers. Like you did one for the current to resistor, and then for general voltage, you want like a screenshot of each of those?
Yeah, so for this particular problem, I asked you to determine the voltage drop over the capacitor, effectively, that voltage V of t, and the current through the resistor. So my expectation would be that I get 2 screenshots, one for the voltage drop and one for the current. And that your screenshot include the schematic and the plot. So effectively what you see on your screen right now, or what you're seeing on my Ltspice screen, is what I would expect to see for the resistor. And then what we did a couple of minutes ago is what I would expect to see for your voltage.
All right, sounds good. Thank you.
Any other questions? All right, well, that's really all I had prepared for today. It's really just for the next couple of weeks, correctly identifying whether or not you have a parallel or RLC circuit or not, determining whether the circuit is critically damped, overdamped, or underdamped, and then applying the table. So hopefully it's fairly straightforward. If me or whoever you had for circuits 1 did a good job of teaching you the transient analysis for first order circuits, this shouldn't be wildly difficult. I guess I'll see you guys on Monday. If you have any questions or anything, feel free to shoot me an email over the weekend, and I can either address them then or we can talk about them in class. You guys have a good weekend.
You do the same. Thank you.